Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Science in Easy English with Oliver and Lily. Could another ice age happen?
It's definitely a question that makes you do a double take.
Oh, absolutely. We are so glad you could join us today because if you take a look at the formidable stack of sources we have sitting in front of us right now, and we are talking about extensive data from NASA, comprehensive reports from the IPCC, and some truly cutting-edge paleoclimate studies, you will see our mission for today's deep dive.
And it's a mission to answer a question that honestly seems almost entirely counterintuitive in our modern, rapidly warming world.
Right. Could another ice age actually happen? Whether you are prepping for a high-level science class, maybe trying to win a debate, or you are just deeply curious about the sheer mechanics of our planet, you are exactly in the right place. We are going to deliver some massive aha moments for you today.
We really are. To genuinely understand the future of our climate and figure out where we are heading, we have to look deep into Earth's history first. We need to decode the mechanisms of the past to see exactly how ice ages are naturally triggered.
It's essentially a journey back in time, right?
Exactly. A journey to understand the immense natural rhythms of the Earth system before we can even begin to comprehend how our current actions might be altering them.
Okay, let's unpack this because before we can talk about the future, we have to talk about the ultimate natural pacemaker of Earth's climate. I am talking about the Milankovitch cycles.
Right, named after the brilliant Serbian scientist Milankovitch.
Yes, Milankovitch. These cycles are, well, they're basically the celestial gears that drive the planet's long-term climate. You have to think of Earth not just as a static rock floating in space, but as a dynamic object that is stretching, nodding, and wobbling as it orbits the sun.
It is a very delicate mechanical system.
It really is. And there are three main cycles you need to know about from the data. First up is eccentricity. This is a massive 100,000-year cycle where Earth's orbit literally stretches. It goes from being a nearly perfect circle into a much more elliptical kind of oval shape. And that physically changes our distance from the sun.
Which naturally dictates how much total solar radiation hits the planet.
Exactly. Then next we have obliquity. This one is a 41,000-year cycle where the tilt of Earth's axis shifts slightly back and forth. It rocks between 22.1 and 24.5 degrees.
And that tilt is what gives us our seasons.
Right. And finally, there is precession. This is a 23,000-year cycle where the Earth wobbles on its axis, kind of like a spinning top that's starting to slow down.
What's fascinating here is exactly why these specific cycles matter so much to the formation of an ice age. Because the key to triggering a planetary freeze isn't actually about having brutal, extreme winters.
Which is what everyone assumes, right? You think ice age, you think freezing cold winters.
I mean, it makes intuitive sense, but it is incorrect. It's all about the summers. Specifically, the summers at the 65 degrees north latitude.
Okay, so roughly the latitude of places like Iceland or northern Canada.
Exactly. If the celestial clockwork aligns so that the summer sun, or the insolation, as it's called in the literature, at 65 degrees north is simply not strong enough to melt the snow that fell during the previous winter, well, that snow persists.
It just survives the summer.
It survives. And then year after year, it accumulates. It compresses into ice, and those continental ice sheets begin to grow.
So it's much less about a sudden catastrophic freeze like you see in the movies and more about a quiet, relentless accumulation over thousands of years.
Precisely. But once that ice starts covering significant ground, it starts changing the rules of the game entirely. It initiates what scientists call the ice albedo feedback loop.
The reflectivity, right?
Right. Because ice is highly reflective, it bounces incoming solar energy straight back into space instead of allowing the Earth to absorb it. So the more white ice you have, the more sunlight gets reflected.
Which cools the planet even further.
Exactly, leading to even more ice. It is a massive self-reinforcing cycle.
Which brings up a really interesting question, because if the cycle is self-reinforcing and the ice just keeps cooling the planet to make more ice, how does an ice age ever actually end?
That is where the paleoclimate sources reveal a highly surprising detail, specifically regarding a period called the mid-Pleistocene transition.
Okay, the mid-Pleistocene transition, what happened then?
This was an era about 1 million years ago when the pacing of Earth's ice ages mysteriously shifted. They went from those 41,000-year obliquity cycles we just mentioned to the much longer 100,000-year eccentricity cycles. And what the research shows is that late in a prolonged ice age, the global climate gets exceptionally dry.
Because colder air simply cannot hold as much moisture.
Exactly. Plus, the vast ice sheets lock up a huge amount of the planet's water. Because it is so incredibly dry, substantial amounts of dust begin to blow across the globe.
Let me guess, all that dust ends up settling right on top of those pristine white ice sheets.
You nailed it. The dust builds up, making the ice sheets darker. This dark layer significantly lowers their albedo, their reflectivity.
So instead of acting like a mirror, they start acting like a dark t-shirt on a sunny day.
That is a perfect analogy. They suddenly absorb more heat rather than bouncing it away.
Huh?
So when the orbital cycles shift and we hit the next natural peak in solar radiation, what scientists sometimes call an uplobe in the insolation cycle, those dirty, darkened ice sheets are primed.
They absorb all that extra energy.
Yes, they melt rapidly, triggering a sudden and dramatic termination of the entire ice age.
That is just wild to visualize. A pristine white ice planet getting completely covered in a layer of grime until the sun finally melts it away. But wait, if dust makes the ice melt faster, shouldn't our current industrial air pollution be triggering the end of an ice age, not preventing one?
That is a highly logical question. In a purely natural cycle, yes, particulate matter like dust or certain types of pollution can lower the reflectivity of ice. We actually see this happening today with soot falling on glaciers.
Right, the black carbon issue.
Exactly. But, as we will discuss shortly, the warming effect of our greenhouse gases in the atmosphere entirely overpowers the localized effects of dirty ice.
That makes perfect sense. The blanket of CO2 is just vastly more powerful than the dust on the surface. But moving from the deep past to the near future, if you scroll through the news lately, you might have seen some terrifying headlines.
There have definitely been a few making the rounds.
I am looking at articles right here from European papers like the Irish Times and Posten, and they are claiming the sun is acting bizarrely. They are prompting fears of a 300-year mini ice age hitting us this very century due to declining solar activity.
Yes, I have seen those.
As our resident voice of reason, what is actually going on here? Is the sun going to freeze us out?
Those headlines are referring to phenomena known as solar minimums. The most famous historical examples are the Maunder minimum, which occurred roughly between 1645 and 1715, and the Dalton minimum between 1790 and 1830.
Okay, so hundreds of years ago?
Right. These were historical periods when sunspot activity was exceptionally low, and they happened to coincide with periods of regional cooling in parts of the Northern Hemisphere. It's an era often referred to as the Little Ice Age.
Oh, is that why you see those historical paintings of the River Thames in London completely frozen over, people ice skating on it? Yeah.
Exactly. That was during the Little Ice Age. Some solar researchers do suggest that we might be due for a similar period of very low solar activity sometime this century.
I mean, the headlines sound absolutely terrifying, but when you look at the NASA data in our stack, how much does solar radiation actually drop during one of these minimums?
It is a remarkably small fluctuation. We're incredibly fortunate that the amount of solar radiation reaching the Earth's surface is highly stable. During the Dalton minimum, the decrease in solar radiation was only about 0.08%.
Wait, 0.08%? That is tiny.
It is. The Maunder minimum was slightly larger, just a 0.25% decline. So even if we were to hit a so-called grand solar minimum this century, the absolute maximum cooling effect it would have on the entire planet is roughly 0.3 degrees Celsius.
And how does that 0.3 degrees of cooling compare to the warming trajectory we're currently on?
If we connect this to the bigger picture, it is barely a drop in the bucket. Human-caused global warming is expected to add anywhere from 1 to 5 degrees Celsius to global temperatures by the year 2100, entirely depending on our emission pathways.
So a 0.3 degree drop from the sun.
A grand solar minimum would not even come close to canceling that out. In fact, a 0.3-degree cooling would only offset about 3 years' worth of our current carbon dioxide growth.
Just 3 years.
Yeah.
That puts it into perspective perfectly.
The data from Skeptical Science and NASA is absolutely clear on this. Human greenhouse gas emissions have an impact that is at least 6 times greater than any prolonged solar minimum. So the idea that the sun is going to plunge us into a new mini ice age and somehow save us from global warming is simply a myth.
Here's where it gets really interesting, though. Because while a global mini ice age triggered by the sun is definitively off the table, the sources do point to a mechanism that could actually cause a sudden, localized deep freeze.
Yes, and it has to do with the oceans.
We are talking about the Atlantic Meridional Overturning Circulation, or the AMOC for short. You can imagine it as a giant, powerful ocean conveyor belt. It acts as a planetary heat pump, bringing warm, salty water all the way from the tropics up through the Atlantic to northern Europe.
It is the primary reason why countries in Europe have relatively mild climates compared to places at similar latitudes in North America.
Right, but the mechanics of this conveyor belt are incredibly delicate, aren't they?
Extremely delicate.
Yeah.
The entire system is driven by differences in water density, which is dictated by two things: temperature and salinity.
Heat and salt.
Exactly. Warm, salty water flows north at the surface. As it reaches the colder northern latitudes up around Greenland, it cools down. Because cold, salty water is extremely dense and heavy, it physically sinks to the deep ocean.
It just drops straight down.
It does. And then it flows back south along the ocean floor, which physically pulls more warm surface water up behind it to take its place. That sinking motion is the engine of the conveyor belt.
But the threat here comes from what is happening in the Arctic right now. As global warming melts those vast Arctic ice sheets and the glaciers on Greenland, they are dumping colossal amounts of fresh water right into the North Atlantic.
Precisely. And fresh water is significantly lighter and less dense than salty water.
Because it doesn't have the salt weighing it down.
Right. So instead of sinking to the ocean floor, this massive new influx of glacial meltwater just sits on the surface. It entirely disrupts the vertical mixing of the ocean. It acts like a brake, physically slowing the sinking process and therefore slowing the entire conveyor belt down.
I was actually looking through the oceanographic data in our stack, and there's this really striking anomaly that keeps coming up. They call it the cold blob. It's just sitting in the ocean directly south of Greenland. Is that actually connected to this conveyor belt slowing down?
Yes. Scientists consider that specific cold blob anomaly to be the literal fingerprint of a slowing AMOC. It is one of the only places on Earth that is actively cooling right now.
Which is crazy when you think about the rest of the map being bright red with heat.
It really stands out. And that cooling strongly suggests that the warm tropical waters are no longer reaching as far north as they used to. However, we have to impartially balance the scientific viewpoints on what happens next, because the predictive modeling varies significantly across our sources.
Right, because some models say the whole system is going to shut down entirely, right? Like a complete collapse.
Some of the more extreme climate models do predict a complete and total collapse of the AMOC sometime after the year 2100. But a recent, highly comprehensive study from the University of Washington took a closer look at actual real-world ocean observations, rather than relying solely on computer simulations.
And what did the real-world data show?
They discovered that the real-world AMOC is actually shallower than many of those extreme models simulated. Because it flows closer to the surface, it is somewhat more resilient to these freshwater changes.
Okay, so it might not completely break.
Their conclusion is that instead of a total collapse, we're much more likely to see a limited decline of about 18 to 43% by the end of the 21st century.
I mean, that sounds a bit more manageable than a total shutdown, but a 40% decline is still a profound shift in a major planetary system. What actually happens to Europe if this conveyor belt does hit a tipping point and collapses?
The impacts would be staggering. Northern Europe would experience severe, rapid cooling. We would see a dramatic increase in fierce winter storms and a vast expansion of sea ice along the European coasts.
That would deeply disrupt agriculture and daily life across the whole continent.
Utterly disruptive. And the truly bizarre part is that this severe regional deep freeze would be happening at the exact same time that the rest of the globe continues to aggressively warm. It is a stark reminder that climate change doesn't just mean a uniform increase in temperature everywhere.
It means chaos.
It means the destabilization of the intricate systems that distribute heat around the planet.
So what does this all mean? When we zoom out and look at the Milankovitch cycle slowly turning, the solar minimums, and these complex ocean currents, are we eventually going to see a global ice age or not? What is the ultimate verdict from all this data?
To answer that definitively, we have to look at a staggering conclusion from a study published by researchers at the Potsdam Institute for Climate Impact Research. They wanted to crack the code of exactly when the next ice age should naturally occur.
Without humans interfering.
Right. By looking purely at the natural orbital patterns, the celestial clockwork we discussed earlier, they calculated that Earth should be due for its next natural ice age in roughly 10,000 to 50,000 years.
Okay, so 10,000 to 50,000 years. That is the natural baseline. But we aren't exactly operating on the natural baseline anymore, are we?
No, we are not. And this is where the sheer scale of human impact becomes undeniable in the data. Anthropogenic, or human-caused, carbon dioxide has an exceedingly long lifespan in our atmosphere. The Potsdam study shows that even if we follow a moderate emissions scenario, meaning we add roughly 1,000 to 1,500 gigatons of carbon to the atmosphere, that lingering CO2 will fundamentally alter the Earth's thermal balance.
To what extent?
It will retain so much heat that it will completely suppress the onset of the next natural ice age for at least 100,000 years.
Let's ground that number for a second. When the study says 1,000 to 1,500 gigatons of carbon, what does that actually look like compared to what we emit right now?
To put it in perspective, the global economy currently emits about 37 gigatons of carbon dioxide every single year.
So the 1,000 gigaton threshold isn't some distant, unreachable number at all.
Not even close. It represents just a few decades of our current industrial output. That relatively brief window of human activity is enough to dictate the planet's trajectory for the next 100 millennia.
That's almost hard to wrap your head around.
The researchers at the Potsdam Institute emphasize that, because of this, humanity is no longer just a species living on Earth. We have quite literally become a geological force.
So we are literally skipping an entire glacial cycle. The orbital gears are turning to trigger an ice age, but our carbon emissions are just entirely overriding the system.
That is exactly what the data demonstrates. Our actions are now operating on a planetary geological timescale. In fact, the director of the Institute proposed that we have entered an entirely new epoch. Instead of calling it the Anthropocene, he suggests it could be dubbed the deglacial epoch.
The deglacial epoch.
Defined entirely by our ability to halt the natural glaciation of the planet.
That is profound. And there is another detail in the stack of sources that perfectly highlights the real-world, ground-level consequences of skipping this cycle. It comes from a study out of Brown University analyzing ancient plant waxes, which sounds incredibly niche. How do ancient plant waxes tell us anything about the Ice Age?
It is a brilliant piece of detective work. Plant leaves have a waxy coating to retain moisture. When a plant dies and gets buried in sediment, that wax can survive for tens of thousands of years.
Just preserved in the mud.
Exactly. What is crucial is that this wax preserves the specific isotopic chemical signature of the rain that the plant absorbed when it was alive.
Okay, the chemical fingerprint of the rainwater.
Right. And the isotopes of hydrogen and oxygen in rainwater differ depending on whether the global climate is in a deep ice age or a warm interglacial period. By analyzing these ancient waxes, scientists were able to create a highly accurate timeline of historical water signatures.
And how does that connect to us today?
They matched those ancient ice age signatures to the water, sitting deep inside our current aquifers. They discovered that a vast, disproportionate amount of the critical water resources that human civilization relies on right now, the groundwater we use for massive agriculture in places like the high plains of the United States, or for cities and industry across parts of the Middle East, is actually fossil water.
Fossil water.
It is leftover runoff from the massive glaciers of the last ice age that has been stored underground ever since.
Wait, so we are actively pumping and drinking Ice Age water?
Yes, we are.
Ah.
And the implication of that finding is sobering. Because we are now skipping the next ice age, the natural mechanism that built up those colossal frozen water towers is completely broken.
The vault isn't going to be restocked.
Exactly. Once we tap into and use up all of these ancient deep water reserves, the Earth is not going to naturally replenish them. We are permanently spending a geological inheritance without any mechanism to get it back.
All right, let's take a breath and synthesize everything we've covered in this deep dive, because we have really journeyed across immense spans of time today. We started by exploring the majestic celestial clockwork of the Milankovitch cycles, learning how the subtle stretching and wobbling of Earth's orbit dictates the natural rhythm of the ice ages.
And we completely debunked the pervasive myth of a solar-powered mini ice ager.
Right, proving that our sun's minor fluctuations are absolutely no match for the heat trapped by our own emissions. We navigated the complex, shifting currents of the AMOC, revealing how melting Arctic ice threatens to slow down the ocean's heat pump and plunge regional areas like Europe into a deep freeze.
Even while the rest of the planet warms.
Exactly. And ultimately, we arrived at the staggering realization that human carbon emissions have essentially hijacked the planet's natural glacial rhythms, canceling out the next ice age for at least 100 millennia.
This raises an important question for you, our listener, to seriously reflect on. We so often think of ourselves as small, as merely inhabitants subjected to the whims of the natural world. But the data we review today paints a vastly different picture. It asks you to comprehend the sheer, unimaginable scale of human influence.
We really aren't just passengers anymore.
No, we are not. Our collective actions have accumulated to the point where they dwarf the gravitational pull of the planets and the cycles of the sun in determining the long-term climate state of the Earth.
And I want to leave you with one final provocative thought to mull over long after this deep dive ends. It's something not explicitly stated in the studies, but it is the burning question that all of these sources inevitably inspire. If our civilization's everyday activities, our industry, our transportation, our agriculture, have accidentally accumulated into a geological force powerful enough to literally cancel a planetary ice age for the next 100,000 years, what might be possible if we actually woke up?
That is the real question.
What if we consciously, intentionally directed that exact same immense power, not just toward blindly extracting from the Earth's system, but toward actively repairing and balancing it? The scale of our impact is terrifying, yes, but it is also proof of our profound capability. Thank you so much for joining us on this deep dive. We hope you walk away today with an entirely new perspective on our planet's deep past, its complex present, and the future we are actively writing. Keep asking questions, keep looking at the data, and we will catch you next time.